Hello student, this is a lecture of physical chemistry. In our previous lecture, we have discussed about the analysis or characterization of crystalline compound by using X-ray crystallography and Bragg's method. Now in this lecture, we will discuss the defects in the crystal structure. So friends, in crystal system, the lattice point atoms, ions, molecule are orderly arranged and occupied stenchiometrically are called as perfect crystal. But in real crystal, there are always some imperfection in their lattice. This imperfectness are called as defect in the crystal structure. That means any deviation from the perfectness in the crystal are called as defect in crystal lattice. Sometimes we can create the defects in the crystal system in order to use this crystal for a specific application. That's why we simply called as crystal engineering. That means we can try to develop defects in the crystal, or we can also minimize the crystal defects in the crystal. We can crystallize or form a perfect crystal also. So these are the is a part of crystal engineering. So let us see why do the defects in the crystal and how they can be minimized. So we can able to create the defects in the crystal, or we can also minimize the defects in the crystal depending on their application. A crystalline solid are formed by cooling a substance in a liquid state, which decrease the kinetic energy or translational energy in the molecules that we know. If the crystallization takes place fast, very fast, then orderly arrangement of the particle is not possible and the defects in the crystal arises. The defects in the crystal can be minimized by carrying crystallization process at very slowest rate so that the orderly arrangement or periodically arrangement of the particles are takes place and we get the perfect crystal. So in crystalline compound there are two types of defects we can produce or we can minimize also. First is point defect, second is line defect. That means the defect created in a lattice point or a particular point. This defect is produced due to the arrangement of the particle in the crystal structure. That means the particle may dislocate their original position, or the particle may be absent or create vacancy in that lattice point or between the lattice space. Line defect. This defect is produced due to the irregularities in a complete row of particle or plane of the particles in the crystal closed crystal structure. So point defect are again further classified into the three types. Vacancy defect, that means there will be vacancy in a lattice point. This defect is created by a scientist Schottky. So these defects also recognized as a Schottky defect. Second is interstitial defect, that means the lattice point may be leave their position, their original position, and it is maybe in between the lattice space, that is interstitial position of the lattice space. These defects also created by a scientist Frankel. So this defect is also recognized, that means interstitial defect is also recognized as a Frankel defect. And third is impurity defect. That means this defect will be created by doping the some impurities in the perfect crystal. So line defects are also two types: edge dislocation and second is screw dislocation. That means the edges are dislocated their original or vertical position, or screws dislocation means a plane of crystals are dislocated their perfectness, so we call as screw dislocation. So in your syllabus only a point defect is are there, so we will discuss only point defects, that means vacancy defect, interstitial defect and impurity defects. So first is vacancy defect. This defect is created by a scientist Schottky, so we recognize as a Schottky defect also. This defect is produced during the crystallization. Some of the lattice point remains unoccupied or vacant by the particle. In this case, the vacancy are produced due to the cation or anion. Then this defect is called as Schottky defect. That means the vacancy is created due to the cation or anion. This defect is called as Schottky defect. In this defect, the density of the crystal lattice is less than expected value, obviously, because in perfect crystal, that means one of the particles or cation or anion are vacant, that means density ultimately is less than expected value. For example, these defects is generally observed in sodium chloride, potassium chloride. If you see the schematic representation, suppose A is cation, B is anion, then again cation anion. So in this way the crystal is formed. So this is the lattice point. So this cation also vacant, that means this lattice point is vacant. This lattice point is vacant due to the absence of an ion. This lattice point is the vacancy is created because of the cation. So this is about the vacancy defect or Schottky defect. So density is always less than expected. So second point defect is interstitial defect. That means this defect is created or recognized by a Frankel defect. In this type, an ions in the ionic solid leaves their regular lattice site or lattice point and occupies a place between the regular lattice point or between the lattice or interstitial position of the lattice. This defect is called as Frankel defect. If you see the schematic representation, that means cation and anion are all are in their regular positions, but this cation is leave their regular position or regular site and goes into the interstitial position of the lattice. So that's why this effect is also called interstitial defect or Frankel defect. Frankel defect is arises in case of ionic solid with relatively smaller size cation which can be fit into the interstitial position of the crystal lattice. This defect is also called as dislocation defect. And in this Frankel defect, only in case of ionic solid, only cation will leave their regular site because cations are smaller size and it is easily occupied in interstitial position. But if you compare with an ion is bigger, so it will not occupy an interstitial position. So this defect is created due to the dislocation of only cation. This type of defect is called as Frankel defect or dislocation defect. The Frankel defect does not alter the density of the crystalline solid because number of anion and cations are the same, so density will not alter. For example, silver chloride, zinc sulfide, etc. So now third is impurity defect. So in this defect, the smaller size impurity may be doped in the regular crystal, so that impurity may occupy their position of the lattice point or interstitial position. So this defect is called as impurity defect. In this type of defect arises due to the cation from its regular site in ionic crystal lattice is replaced by the different cation. That means that is regular cation will be replaced by the other impurity cation. If the impurity cation is substituted in place of regular cation, then it is called as substitution impurity defect. This example, alloy of brass, that is copper and zinc. So we get that regular copper will be replaced substituted by the zinc. So we get a new type of material called as alloy, and we called as brass. So that have specific application of this alloy. So by creating this type of impurity defect, so we develop a new type of metal. So that is very important. Second impurity type defect, if the impurity cation is present at interstitial position, then it is called as interstitial impurity defect. The interstitial impurity defect changes their property of its original crystalline solid. So good example for this defect is interstitial impurity defect is stainless steel. So if you dope that carbon in the interstitial position of the iron, so we get the new material of iron and carbon. So this material is called as stainless steel. So we know that the application of this material, novel material, that is stainless steel, we can use this material for very better application. This material having shows the better property than iron also. So that's why the defects in the crystalline compound or crystalline solid or solids also have a lot of applications. We can make the different alloys, we can make the different metals, other type of materials that we can develop for their specific application by creating the impurities defects in the crystal. So that's why this specific division we call as crystal engineering is very important part of the solid state chemistry. So here we stop the lecture. In next lecture we will see the second property of the crystal solid, that is liquid crystalline property and their application. Thank you.